Hello, and welcome to Lab 4, Raw Physics, Spring Mass Lab. The main objectives of this report is to analyze the X and Y positions from the video, compute the spring's stiffness and initial position, make a model using the information found, and compute the energies, which are the kinetic energy and the gravitational energy and the spring energy. After that, we compare in the display window the predicted motion and the observed motion of the mass, and plot in the graph window the energy changes that I computed in the model. Here's the video that I analyzed in Tracker. I set the coordinate system at the fixed attachment points with the positive y-axis pointing up and the positive x-axis to the right, and the calibration stick from the fixed attachment point to the center of the object, which is 70 centimeters long. I started tracking from frame 5, which was when the object was about to move, and here's the video. And this is the y position versus time plot, and the x position versus time plot. And here's the system properties that we know. The mass is 0.402 kilograms, and the length of the spring at the static equilibrium state when the object is pulling it down is 0.7 meters, and the initial position is minus 0.112 for the x component, and for the y component minus 0.638 meters, and the oscillation period is 1.519 seconds. And here's the system properties that we want to know. With the little algebra, we can find that the spring's stiffness is 6.878 newtons per meters, and the relaxed length of the spring, which is 0.126 meters. And here's the equations used in the code we're about to see. You can pause the video if you want to see them. So here's the code. The mass of the object is over here. Get the initial conditions from Tracker, the time step and the constants, the relaxed length and the current length, and the energy equations, and here's the force equations and the net force, and the predicted velocity and position of the mass. So first, let's see the model, a prediction versus the observed in the y and x components of the position. As you see here, they are almost identical. It's a bit off here and here, and that's because there's a drag force acting on it, and we did not account it. We assume that there's no drag force acting. So now let's see the energies graph. The energy graph looks fine because the total change in energy is zero or almost zero. As you see, if one of the energies goes up, the other goes the other way down, so the total change in energy is almost zero, and that's what we expect. What does it mean for your model system? Is the energy principle satisfied? As we see here, the total change in energy is not always zero, and that's because we rounded some of the numbers in our calculation. And as you see here, it's a very small number, so it's almost zero. So yes, the energy principle is satisfied and the energy is conserved. Using the data you obtained in Tracker, make two separate estimates of oscillation periods. Compare the two estimates and discuss. So here's the period of oscillation for the x and y position, x and y components of the position, and they are different, and, and that's okay because the velocity has two components, the x and y component, and they are different from each other, and that's why we have different period of oscillation. So it's moving in two dimensions. The x here is larger, and that means that the x component of the velocity is less than the y component, or that the distance traveled in the x position is farther. Conclusion. I analyzed the video of a spring mass system, got the parameters needed to make a model using VPython, then compared the observed position data with the prediction data, and showed a graph of the change of the energy. Explained if the energy principle is satisfied, and made two separate oscillation periods, the x and y. Explained the difference and why. That was lab 4. Thank you for watching.